Good,
Good afternoon.
good afternoon. That was Felicia, I believe. Good afternoon, everybody.
Good afternoon.
Good afternoon, Caroline. Awesome. Good afternoon. And good afternoon. And good afternoon, Kevin. I like that. Whoa. Oh, I get it. Right. Hollywood. Very cool. I was like, whoa, that's like such a, where did he get that image? I mean, I still don't know where you got it, but okay. Good afternoon, Amanda. Okay. Good afternoon. Sorry. Okay. Not to the chat. Good afternoon, David K. Good afternoon, Amanda, even though I just said that. Okay. Good afternoon, Amy. Good afternoon, Caitlin. Oh, now I'm really okay. So sweet lid, comma, yo. Okay. We all have to do whatever we can to distinguish ourselves. Oh, I should open up a portal for clothing? No, that would be totally inappropriate. Okay. Good afternoon, Jamalette. Good. Oh, more people are coming. Okay. Good. Who did I just say? Hi, Christina. Good afternoon, Chloe. Ooh, sorry. Good afternoon, Amy. Good afternoon, David P. Or did I just, why do I feel like I just said that? No, because I didn't. Okay. Good afternoon, Sophia. Good afternoon, Alicia. Good afternoon, Savannah. Awesome. No, it's like, I feel like it's like a rock concert. Good evening, Savannah, Georgia, wherever you are. Okay, wait, someone just came in. Did I just say rock concert? Does anyone even call it that anymore? Wait, there's someone in the waiting room I know, but I can't get there. Oh, there. Okay. Good afternoon, Kevin. And happy Halloween, Kevin. Okay. Awesome. All right, we're gonna get going. We're the reward for being you guys, people, is that we're actually, because we are beginning, I almost feel like we're making up time. We're making up time that feels like it was lost, even though it's never lost. It always goes the same place. What I mean is, in a second, so what we're going to do, we're going to continue actually going through homework 6, which was just assigned and which you haven't even done yet, and which technically isn't even due till Monday. But I'm going to keep, but this time we're going to go in the opposite order. I'm going to work it through with you as much as I can, not all of it, but we're going to keep. So hopefully I'm saving you guys time and stress. That the things I'm going to talk about today are in the context of homework 6. So you could totally write them down and you could totally use these ideas to help you fill out homework 6. That would be encouraged, not discouraged. Hold on. So yeah, and it's all about, but again, stop me with any questions or anything. It's all about, so I don't remember what the title of homework 6 is, but everything I'm going to be talking about today, I'm going to be specifically talking, hold on, I always have this screen schizophrenia, or I shouldn't use that word like that. I always, have this screen management issue. Like, what I'm going to be talking about is homework 6. I just lost it. I have it on the other screen. Is homework 6 problem, like, because I think at the last minute, we actually did finish a problem yesterday. I think it was problem 2. What I want to talk about, here we go. I want to talk about, homework 6, excuse me. Homework 6 is called Big Old Duck. The most important problem on homework 6 for sure, the ultimate problem that everything's sort of working toward, is the very last one, which is called Big Old Duck. I will certainly talk about that in class, just not yet. Again, not to get people riled up, but when we ever have an exam, Big Old Duck will almost undoubtedly be like a problem on that exam. And again, I'm not trying to put it off. When we get to it, we'll talk about it. You won't be, the exam will just come out of nowhere with a surprise. Will not just be a surprise. But what I want to talk about today in homework 6 is problem 4. Switch the screens in a moment, but it's problem 4, which is called a velocity time graph. Okay, that's what I'm going to talk about today. I believe we finished the problem 2 yesterday. But what it is that we're talking about in general right now, again, just to sort of keep the material organized, hopefully somewhat coherent for you in your mind. Like, we started the year with the concept of velocity. Then we moved to changes in velocity known as acceleration. So put in calculus terms, we started the year talking about the first derivative of position with respect to time. Then we moved to the second derivative of position with respect to time. And now we're holding our attention there. Like if this were a math class, a pure math class, we could then move to the third derivative of position with respect to time, and then the fourth, etc. But it turns out that in nature, in the physical world of space and time, a lot of interesting and common and analyzable things tend to happen on the second derivative level. You'll see more and more about why that is in the course, in the rest of the course. But so a lot of phenomena that are worth studying, a lot of motions that are observable and measurable, tend to demonstrate an acceleration, that is a change in velocity, but they don't tend as dramatically to demonstrate a change in acceleration. So we like fix our attention, we hold our thought process on what happens when there is a constant acceleration, when there's a change in a change, but no change in that. Right. And again, I'm going to keep saying that because it's like, I can be as confusing as it can be interesting. We're looking at changes in changes, but we're looking at constant changes in changes, right? Constant acceleration is our context right now. Now, a very specific example of constant acceleration. So we're looking at situations where A equals A naught. More people coming, sorry. We're looking at situations where whatever the initial acceleration was is the acceleration at every moment along the way, which is to then say whatever the acceleration is at any moment is the average acceleration, and vice versa, because there's just one number going all the way through. So we're looking at situations where we have this advantage of knowing that the initial acceleration, the instantaneous acceleration at any moment, and the average acceleration are all one number. That's what we're looking at in general. And then more specifically, where we sort of got to yesterday is the classic example, the super central physics example of this kind of constant acceleration is free fall near the surface of the earth. So what we're really talking about now, really, in many of these exercises and problems, what we're really sort of analyzing is what goes on during free fall. Okay, and sometimes we're analyzing it directly, and sometimes we're analyzing it by analogy. You'll see what I mean in a moment. But what, and so anytime we're talking about free fall, any and all of the equations on this page all apply. This page right here, for the first time, not one equation on this page is new anymore. I mean, they're new, but like they're not goals. We've now seen every single one of these equations on the board right here. They are not our full list of all the equations of the year. They are our full list of all the equations. Well, at least the last three are all of the equations that apply when acceleration is a constant. And then what I'm saying now is specifically when we're in free fall, the value of that acceleration constant is what we refer to as lowercase g, okay? Lowercase g. If you're measuring in meters per second squared, then that's generally around 9.8 or 10 meters per second squared. If you're measuring in feet per second squared, it's 32 feet per second squared. If you want to measure in miles per hour per second, and I'll say more about this again. I mean, if you, which is even an unusual but a very intuitive way to talk about G. You could then you convert it and you find that G is approximately 22 miles per hour per second, right? In other words, what I'm saying is you want to picture what happens if you just drop something. If you drop something, yeah, we're saying every second it gains speed at a rate of approximately 10 meters per second. But most of us can't really relate to meters and seconds as intuitively as we relate to car driving speeds and stuff. So just for perspective, what we're saying is if you drop something from rest, in 1 second, it'll be going 22 miles an hour, 22 miles per hour. Then at the end of the second, it'll be going 44 miles per hour. Then at the end of the third second, it'll be going 66 miles per hour. I mean, that's just a unit conversion. You can check it yourself. But so I'm saying you drop a rock in 3 seconds, it's going to be going like in 4 seconds, it would get a speeding ticket on a highway. Like that's how dramatic gravitational acceleration is, just if that puts perspective on it. But so we're going to be studying, but I don't really care what the number is as much. Like, it's not a matter of memorizing the number, because the number changes depending on what units you're talking about and depending on how many significant digits you're going to, blah, blah, blah. The key point is not that it's a number, but that it is a constant number that we can always rely on. And so we just call that constant lowercase g to signify that we're talking about free fall. One last thing you'll notice it says on this. So we're going to be talking more about free fall today. Notice on the sheet, it sort of cutely or maybe confusingly says free falling up. What I want to emphasize in the problems we look at today, I'm not just going to be talking about free falling up. I'm talking about free falling down as well. But I want to emphasize that free falling up is a thing. Like, please remember from Monday's class, the definition of free fall means an object that is subjected to no influence at all other than gravity, right? An object that's not being pushed or pulled or touched, contacted, interacted with any other object other at all. An object that is just being pulled toward the center of the earth in this through empty space in this way that apparently the center of earth has the power to do. So free falling is a state that you could be in just as easily while you go up as while you go down. Or free falling is a state you could be in as you, if a quarterback throws a football and the football is like arcing across the field, you could tell I'm like a real, I mean, obviously I know a lot about football. You could tell just by looking at me, but if you throw a football and it's going, or you shoot a cannonball out of a cannon and it's making a, and it's projectiling across the field, and we're going to study that in more detail as well. Even though it's going somewhat up and somewhat horizontally and going at some funny angle and curving the whole time, that entire experience is called free fall. Fall does not have to mean that you're plummeting straight down. It doesn't mean that your velocity is pointing straight down necessarily. What free fall means is that your acceleration at all times is pointing down, that at all times you are changing your velocity in a downward pointing way, meaning that if you, now we go back to like one of those review problems from 2 sheets ago, remember to have a velocity, to increasingly change your velocity in the downward direction means that if you happen to be going down, let's say we call down negative, okay? That means if your velocity is negative, if you happen to be going down, if you happen to have negative velocity numbers, then they'll be getting increasingly negative. You would go like negative 30 meters per second, negative 40 meters per second, negative 50 meters per second. You'll be going increasingly fast. Your speed will be increasing. But if you happen to be going up, if you happen to have a velocity that's pointing up because a moment ago somebody threw you, a moment ago somebody gave you an initial velocity, now you're traveling up at this moment, but nothing is touching you, nothing is pulling or pushing you other than planet Earth. If you happen to be going up at that moment, first of all, we still call it free fall. I'm just trying to emphasize that. You could be moving up, but free falling. Your velocity could be pointing up, but your acceleration is necessarily pointing down, which would mean if you happen to be going up at this moment, if you happen to have positive velocity numbers, they're going to get decreasingly positive. Like, it means that your velocity numbers are always heading toward the negative. So you'd be going like positive 40, positive 30, positive 20, positive 20, positive 10, positive 0, right? And then you would stop for a moment. And then your velocities would go into the negatives, negative 10, negative 20, i.e. you'd start coming down. That entire experience of going up while slowing down and then coming down while speeding up, that whole thing is called free fall. And we're going to analyze this mathematically in a second. If you think about it, that entire thing, that if I throw something up and it goes up and it comes down, my velocity numbers will be changing continuously the whole time. But they'll always be getting negative more and more. They'll always be getting lower, assuming I call down the down direction negative, which is my choice. They'll always be getting more negative, and always by the same amount. So it's a constant acceleration. Your acceleration will be like, say in this example, negative 10 meters per second squared the entire time, whether your velocities are up or your velocities are pointing down. So I just want to, so we're going to look at some examples of that today. And I'm just sort of cutely calling them examples of free falling up, just to emphasize that free fall is a term that refers to the nature of your acceleration. It does not refer to the nature of your velocity. Okay, that said, I'm going to, oh, there's something in the chat. I'm sorry, I'm going to just switch. I'm going to get ready to go here. I'm going to look in the chat. It might be a hello, but it might be not. Oh, I love when he does that. That is so awesome. Okay, other people can do that too. Thank you. Even if he's just doing it to me, whatever, I totally appreciate it. All right, cool. Thank you, Nicholas. And I'm going to fill out a portal. I keep saying that. Remind me to make a portal. All right. So now what I want to go to, is it worth switching the screen? I'm going to, maybe if you want to put in private chat, like I'm about to go. Okay, I'm about to walk through a problem that you have in front of you, but you have not necessarily started because it's not due till next Monday. I'm not expecting that you've already thought about it. I'm expecting that you can look at it now, and then I'm going to talk about it, which again is problem 4 in home. Problem. Sorry. Problem. Oh, I have so many windows. You know, when the electrons in heaven close a door, they open a window. Hold on. I'm sure that's what Steve Jobs wanted us to believe. Wait 1 second. But so I'm going to go to this. Yeah. Okay. So I've got to open up my speed. Someone sent me a private chat. If you would prefer that I open this up in a screen share, at least so you can see it and screenshot it for a minute, let me know. But if I don't get a private chat to that effect or some kind of chat, I'm just going to start doing. Oh, hello. I'm going to do. Okay. So this is homework 6. Problem 4. Now I'm using this problem to talk about with you. Hold on, I'm gonna look in the chat to see if anybody did ask me to do that. Oh yeah. Oh, okay. Oh, okay. Yes. Okay. 1 second. Okay. So I'm going to talk about this problem now. It seems like people in the chat are okay with like me just. You all know where I am on problem 4 of homework 6. Now, I also want to warn you, this is not me going over the homework, right? Like you haven't done it. So this is not a matter of like me doing the 5-step method. I'm hopefully sort of am doing the 5-step method, but I'm going to say things about, I'm using this problem to explain things. So you'll definitely get the answers from what I'm saying, and it'll definitely make it easier for you to do, I hope. But I'm using it as an excuse to talk about it. So not everything I say do you have to turn in, and not everything you have to turn in will I say. If that, okay, just hopefully this is in the context of problem 4. Hopefully it's help. So, and I keep losing the window. It's so frustrating. Okay, here we go. So it says, okay, well, it says to do this. I guess this is. It says to make a velocity time graph. And it says to basically do this. Oh, and someone's here. Pardon me for a second. I will. Okay, this is supposed to be a straight line, but Okay. Okay. First of all, okay, so it asks in the problem, again, I'm looking at problem 4. It asks in the problem for me to just make a sketch where velocity of a graph, where velocity, instantaneous velocity is on the y-axis and time is on the x-axis, right? It asks me to make a straight line graph. So this is like an unusual thing. Instead of giving me the information and asking me to make a graph from it, it's just like describing the graph. And then we're going to hopefully be able to understand the information from that. Okay, so it tells me to draw a straight line of slope -4 and y-intercept of 12, right? So again, stop me if I've done this wrong in your opinion, but I don't think I have. So I've drawn this straight line, right? Its y-intercept is 12, so so I did do it wrong. Someone should have corrected me. So I should have said, I'm sorry. So I mean to say 0, 12. Where are you guys? Come on. No. So I have the y-intercept is, the point 0, 12. And then I have this other point on the graph 3, 0. Like, how do I know that? Because the slope is supposed to be -4, right? So the rise over the run is supposed to be. So in other words, the rise over the run, the change in velocity, because that's what's on the y-axis, over the run is supposed to be -4, specifically. Right? You see what I'm saying? Like, so I have a graph where the axes are labeled, where the shape of the graph is clear, like it's a straight line, and at least one, in this case, 2 key points are labeled, right? I have 2 points labeled here. And from that, I can see a sense of scale and all that. So let me first start by saying, this is what I consider to be a physics graph. Honestly, a point, especially if you're not in the lab, if you're in homework or exams or whatever, and anybody ever mentions sketch a graph or provide a graph or whatever, what we're looking for in graphs in physics is axes that are labeled so that you know what the graph is of, a clear shape, like is it a straight line? And if it's not a straight line, if it's a straight line, essentially how straight, like how steep, what's its slope? You were looking for, is it a straight line? And if it's not a straight line, if it's curved, then how curved? Like, is it parabolic? Is it cubic? Is it a sine or cosine graph? We're looking for basic shape to be clear. We're looking for axes to be labeled. And then we're looking for a point or two, a couple of points that are signature points that just make the scale of the graph super clear and make things like the particularity of the shape clear. Like in this case, we know we have a straight line. I can immediately see the slope of the line if I see that those 2 points that it connects are the points 0, 12, and 3, 0. So that is a graph. A graph is not a scatter plot. I mean, unless you're like literally making it in the lab, we don't need 1,000,000 points at all. And we definitely don't ever need we never want connect the dots, right? We want a smooth as possible trend that is clear and a couple of points that make the details and the scale of the trend clear. So this is a graph. This is a very informative graph as far as I'm concerned that we now have. Now, I want a couple of things to notice right away. Okay. first thing I'm saying is I want you to know, this is where axes become so important, okay? If we had here a position time graph, which we don't, if we had position time graph, then the slope of any line connecting any 2 points would be the average velocity of the object. That's if we had a position time graph, because slope always means rise over run, which means change in the y or difference in the y values per difference in the x values, right? And on a position time graph, instead of abstract variables y and x, we have position and time, x and t. So the rise over the run on a position time graph is the change in x over the change in t. That's what we know as average velocity, right? In other words, the rate of change of position with respect to time is velocity. Here, we're already graphing velocity. So here, this is as though we had a position time graph and looked at the position time graph and took a bunch and went to time number 1, asked what the slope of that graph was, and made that our new y value. Then we went to time number 2, asked what the slope of the graph was, made that our new y value, et cetera, et cetera, et cetera. So we constructed, in effect, it's as though we constructed this graph from the slopes of an original position time graph, which I don't see here, I don't have, right? But I'm not saying we literally did that, but we could have done that, or that's what this information represents. This velocity time. So this does not tell us directly where anything is in any moment. It tells us how fast it's going at any moment. These are the slopes of the position time graph. But the slope of this rise over run, change in the y-axis value versus or per change in the x-axis value. Well, in physics, in this case of this graph, the y-axis is velocity. The x-axis, the horizontal axis, is time. So rise over run here means change in velocity per change in time. So the slope of this graph between any 2 points is acceleration, right? It's all like one big kind of analogy. Like velocity is to position as acceleration is to velocity. They're all rates of change of one another. So this graph right here, if you're following me, you're probably bored because you're like, yeah, I got it. So what's your problem? So this graph right here, if it has a slope of -4, what I know right away, I'm saying this is a graph of some object that has a constant acceleration of -4 meters per second squared and has an initial velocity of +12 meters per second squared, right? I mean, that's what this graph is. And it's a graph that gives us information for like at least 6, well, the way I've drawn it, for like at least 6 seconds. In fact, to be super clear, like this point down here, hello. Ayo, this point here would presumably, if this is all what it's supposed to be, this point over here would be the point 6, -12, right? This whole graph is giving me like 12 seconds worth of information. What's going on in this graph? Now, is this telling me like where something is at any given moment? No, not explicitly. It's telling me how fast it's moving and in what direction at any moment. This is a graph of, to cut to the chase, this is a graph of what it looks like. This is what it looks like to throw something up and have it fall back down to the same spot. Like, this is an analogy now. This is why I said before, analogy. This graph happens to have a constant acceleration of -4. A constant acceleration of -4. Notice the acceleration is -4 in the first section of this graph when the velocity numbers are positive and getting decreasingly positive. Then the velocities hit 0 and they keep going down. They keep losing at the same rate, at the same steepness. The velocities go from positive numbers to negative numbers because they're always losing 4. They're always losing 4. So this is something that's going forward, slowing down, then stopping, and then coming back faster and faster and faster. This is exactly what would happen if you throw something up, and then it would reach a peak height and then fall down. The only difference is if you throw it up near the surface of the earth and we're measuring in meters and all that, the acceleration would be -10, more like, rather than -4. So like this is exactly the shape, this is exactly the trend, this is exactly the pattern. It's just using the number 4 as an example rather than the number 10. So, but the key point is that the number 4 is negative for this entire thing. The slope is negative for this entire thing, even though the velocities go from positive numbers to negative numbers. So this, I'm just going to say, first of all, this. Okay. Okay, one sidebar. Remember Galileo and all that. I have to make a choice of coordinate system. I am choosing to call in this situation because more than one direction is involved. I'm saying this object is going one way and then it's going another. I'm going to call the up direction positive and I'm going to call the down direction negative. Or in other words, I'm going to call the first direction this thing is going positive and the second direction negative. And so I'm saying, what I want you to see is that even though the graph just goes, whoop, the graph is monotonic, the graph is never changing direction. It is nonetheless, if you follow the fact that this is a velocity graph, it's not a position graph, it's a velocity graph. Therefore, this is depicting an object that actually makes a round trip that goes in a positive direction until it stops and then comes back in a negative direction. And notice it turns around even though the acceleration never flips direction or something. In fact, it turns around because the acceleration does not flip direction, because the acceleration is initially in conflict with the velocity. Initially, the velocity is positive, the acceleration is negative, they're in conflict. So what that really means is the acceleration is pulling the velocity in the opposite direction until the velocity runs out, comes to 0. And then they end up matching. And then we have speed up. So anyway, this is literally what a graph of a round trip under free fall would look like. And you don't see the roundness in the graph, but that's what would happen. So, okay, that said, I'm going to go on with the problem. I mean, I'll get to a question maybe someday. Okay. Oh, yeah. All right. Okay. So now question. Okay, so the object is called Edna. I don't know why. Okay. So we have all right, I'll say, just to be clear, sorry. If I were doing this like 5-step method, see diagram above, right? We just drew the diagram. Okay. So now the question is, assume T is 3. We want to know the first thing, like find X. So I'm reading question A. Question A is determine the displacement of this object for the first 3 seconds of the object's journey. Okay. All right. This is a really good question. I mean, it's an important question. In a way, we've practiced this question now twice, like the very last problem we did yesterday, Monday, the ramp problem in a way was a practice of this. Also, the bicycle problem from last week, like how far does a bicycle get in the first second? All the same problem, which is how far does something get in a certain amount of time if what we know about it is its rate of acceleration, rather than if we knew its average velocity. Okay, super important question. Super doable, super straightforward once you get it, but can be surprising to people the first few times they do this. Like I'm going to use the graph. I'm also going to make comments about the graph. It says determine the displacement of Edna for the first 3 seconds of her journey. Okay, the first thing I want to say is if you're following what's going on here, and this kind of like someone wrote me an email like last week, this is kind of like the email that someone wrote me. If you're following this at all, the first thing you want to realize is sure, we might use our graph. The graph may be very, very helpful, but what we don't want to do is find like we're not looking at the x-axis at time going over to the 3. We're not going to read it directly off the graph. Like at the graph, if I look at the graph, at time equals 3, if I just look at the graph and look at what's happening at time equals 3, I'm going to see a dot on the x-axis. I'm going to see that when time equals 3, the value of the graph is 0. Now, that's certainly important information, and that's certainly real and true. But I better not think that that's my answer. Like my answer to this question cannot be read explicitly directly off the graph. The answer to this question is not 0. Why is that? Well, number one, this is not a graph of displacement. Right? The first real thing we're trying to say here is velocity information and acceleration are very important, but they're 2 different types of information. And what we're now asking is displacement. You might, in early stages of your life, you might think distance equals rate times time. What we're really here to tell you is in some ways, all of physics is an exploration of that idea, distance equals rate times time. But the first big lesson in physics is, no, it does, like the first big lesson in physics is what kind of rate are you talking about? Because if anything, distance equals a rate of average speed times time. Now, hey, that's true, but it certainly doesn't equal a rate of average acceleration times time. And the rate that we have here is a rate of acceleration. And what we built from it is a graph of velocities. I do not explicitly know how far this thing got in 3 seconds. Okay, that's the first thing I want to say. Now, it doesn't mean that my graph isn't helpful, but I'm just saying you can't read it directly off. Okay, that's number one. Number two, maybe I shouldn't be spending so much time on what isn't true, but number two, you might think, okay, 3 seconds. You might think, wait, do I want to do this? Hold on, let me think. Someone might think, well, yeah, someone might think, okay, it's going for 3 seconds. And the rate that was given was -4, like it's accelerating at a rate of -4. So it does that for 3 seconds. So I guess its displacement is -12. And I'm not even going to write that down. If you think something like that, then you are a good person and you are with me and you are still paying attention in class and you are trying. I mean, seriously, but that's not right. It's not good enough. Like it's a good first thought, but it's not right. Like don't say 3 times -4 equals -12 meters, and that's my answer. Why? So I'm saying, first of all, the answer is not -12. If you multiply, I'm just trying to think what I want to write down and what I don't want to write down. If you, so I'm going to start writing things the correct way down in a second, but well, yeah, okay. If you multiply 3 times -4, what you're doing is multiplying a time by an acceleration. And what you're getting is therefore a final velocity. Now that's very important, but that's not where the thing is. That's how fast it's going. And that's all we, so let me show you what we can say is that its displacement equals, if you were, say you know enough to know that this is not easy, say you're in the middle of an exam and you know enough to know kind of what I just said, that the straightforward, simple, fast things that you might want to do are not going to work. So you know enough to know that, but you don't quite know what to do. Again, this is where the 5-step method always comes into play. And we're getting now into some physics where I feel like some of you might feel that way, where you might be like, I get now what's going on just enough to know that it's not always obvious, but I don't quite, and I know once he gets me started, I can go, but I don't quite know how to get started here. So what I'm trying to tell everybody is the way to get started is to get over the idea that you have to see the finish line in order to start. You don't have to see the finish line in order to start. You just have to start. So what you start with, instead of trying to solve, trying to write down relevant things and then making them true, you start with things that just are true and you try to turn them into things that are relevant. So, I mean, I'm going to start with my good old thing that's always right. Average velocity equals displacement per time, right? And then I'm going to rearrange it. I'm looking for displacement, right? So I'm going to rearrange it. So I say displacement equals average velocity times time. Okay, that's true. I'm also going to, because I have no reason not to, I'm going to assume that this thing started with an initial velocity of positive 12, but what position it started in life, I could choose my coordinate system, Galileo. I can say that wherever this thing started, I'm calling 0 to make my life easy. Wherever this object started, I'm going to call that, because I could put 0 wherever I want, Galileo. So I'm going to put 0 wherever this thing started to make my life as easy as possible. That's the whole deal of Galileo. You have to make choices, but you make choices to make your life easy. If you're still with me and you're still paying attention, you might even say to yourself, you know, this whole 0 thing kind of annoys me, because like, I feel like Avogadro's always sort of just turning x0 into 0. So like, what's the point of the x0 thing in the first place? Or you might be saying, is there ever a time that I can't just make x0 0? Good question. Glad you asked. Oh, I see. Watch this. Oh, in the direct chat, 3 people just asked me, wait, is there a time when x0 isn't 0? No, I just totally lied. Nobody did that. But couldn't I do that and make everybody feel that? I've never thought so. Okay, anyway, if you're at all direct thinking, wait, is there ever a time that I can't make x0 0? Like, why would I ever not want to call x0 0? Good question. And the answer is this. As long as you only have one object in your problem, as long as there's only one object, you can and should always say that wherever it starts is what we're calling 0, and then proceed from there. It's just that sooner or later, we're going to have situations where we have more than one object in the problem, starting at different places. So then you'd still make one of them wherever it starts be 0, but then the other one can't be starting at 0. So whatever equations you write for the other one, x0 has to be something. That's really the purpose of the term, is if you're comparing things, okay? But we're not comparing anything here. So I'm going to call that 0. So I'm going to say, fine, displacement equals average velocity times time. Displacement equals average velocity times time. This is where, if I'm not careful now, I might just like plug in 4 for the average velocity and multiply by 3 and say 12. But if I'm being careful, I realize, wait, average velocity is not 4. I don't know what the average, like acceleration's 4 or negative 4. I don't know what the average velocity is. How can I get the average velocity? The way to get the average velocity is to realize that acceleration is constant. Acceleration is constant. So the average velocity is the average of the velocities, right? I'm going to the next, right? Now, right now I'm doing this a slightly slow way just to be as clear as I can. When I'm done with the slightly slow way, I'm going to show you the faster way, and you can do whichever one makes sense. But I think this is the logical way. I'm saying, okay, I'm just I'm assuming that I don't know how to do this. I'm trying to show, like, and again, of course, I'm boring some people. Of course, some people don't need this, and other people I'm losing anyway. But at any and all times, when I'm really trying my best to show any of you is not just what to do, but what to do when you don't know what to do, right? That's really the secret of scientific scholarship and research and whatever, is knowing what to do when you don't know what to do. Right. So what I'm saying here is I don't know what to do. Like, I know I have to get displacement. I know I don't have the basic facts that seem clearly needed for displacement, but I'm just walking through the things I do have. I know that displacement is average velocity times time. I don't have the average velocity, but I know something about average velocity. I know that it is the average of velocities when acceleration is constant. So x equals the average of velocity, v initial plus v over t, all times t. So I'm going to the next page, and I'm just going to recopy that. So I have this. And addition is commutative. So if I keep writing the v naught and the v in different orders, I apologize, but either order is fine. Right? Now, v initial, just to be super clear now, these are two different v's. What do they mean? Well, v initial is v, at 0, which is equal to 12. That was a given. What do I mean by v? V means v final, or instantaneous v final. That doesn't mean at the end of the whole problem necessarily. It means v at the final moment of this interval that I'm looking at. In other words, v means, just to be super clear, means v at 3, right? That v final means the velocity that is attained when we hit moment 3. Now, that I don't know specifically, or I mean, it wasn't like given in the problem, but that is what I can either read off the graph. Yeah, that I can read off the graph or even verify with an equation. Like, if you're following me, if you just look at the graph, I think what v is, the instantaneous v at time equals 3, I think it's 0, right? I mean, I think that's what the graph is saying. That's not the answer to this whole question. That's how fast the thing is going at 3 seconds. But also, if you just step back and think logically about what we're saying, I think that makes sense. Like, we're saying, picture this whole thing is, you could picture throwing something forward at throwing something forward at 12, but knowing it's always, always, always losing 4, even when it runs out of speed, it's still losing, so it loses the negative. Or more, just picture throwing something up. We threw it up at 12, but picture that we're not on Earth, we're like on the moon or something. We're even a smaller Mercury. We're or no, bigger than whatever. We're somewhere like Mars, where the gravity is smaller than it is here, but still existent. So we threw something up at 12, but it's losing 4 every second. So it's like going 12, and then it's going 8, and then it's going 4, and then it's going 0 3 seconds later, right? And then it would start coming down. It would start going into the negatives. That's what the graph is trying to tell us, right? But if you don't, so I think the graph is saying that the velocity at time equals 3, the velocity at time equals 3 is 0. But if you don't like that also, or if you want to see it equation-wise, I could say, remember, the definition of acceleration, the definition of average acceleration is change in velocity per time. So I can rearrange, and we know that average acceleration in this case is the same as it ever was, right? So I can get rid of the bar. So I can say AT equals V minus V naught, and therefore, and what am I solving for? I'm solving for V, so AV equals AT plus V naught. And notice V naught is not 0, right? X naught is 0 because I said so. V naught, it doesn't start with no speed. It starts with 12 meters per second of speed. Is that possible? Sure. When you throw something, it comes out of your hand. If you start your stopwatch, the minute the thing comes out of your hand, it comes out of your hand with 12. And if you're thinking, wait, doesn't it really come out with 0? No, it doesn't. Like it was 0 when it was sitting in your hand, but then your hand moved and gave it speed. And so it came out of your hand. If it came out of your hand with 0, it wouldn't go anywhere. It comes out, if you start your stopwatch, the moment the thing comes out of your hand, it has some sort of upward velocity, in this case, 12. Right? So not 0. So now I'm solving -4 meters per second squared times 3 seconds plus 12 meters per second, right? So we get -12 plus 12 equals 0, right? I'm just using the equations that I have to walk step by step by this. So I'm saying one way or another, hopefully you see, like, stand back. Don't just get so caught up in the trees that you don't see the forest. The forest is I threw something up, like all this is trying to say is I threw something up at 12, but it's losing 4 every second. So 3 seconds later, it's run out of speed. It's got 0. Now, again, because it's got constant acceleration, it doesn't stop forever when it hits 0. When it hits 0 velocity, it doesn't stop forever. It keeps losing velocities. It goes into the negatives. What does that mean? It comes back. That's what happens when you throw something up. Like the speed, the velocities are always going down, always, from positive numbers to smaller positive numbers to 0 to negative numbers to bigger negative numbers. If you want to talk about speed, then the speed is going down and then it's coming up. But the velocities are always going down. Constant acceleration, right? So now what does this do for me? So what this now says is, now that was like it's not a sidebar, it's not irrelevant, but it was like a nested thought process. Now I have the final velocity at the end of the 3 seconds. So now I can go back, like I'm going to go back up to this up here on the next page. I'm going to say, okay, so back to displacement. So I did that. I used acceleration to get velocities. Now I'm going back and using velocities to get displacements, which was the original question. I'm saying this. So now I'm saying, okay, the thing started at 12. It descended, it slowed all the way down to 0. It did it in 3 seconds. So this thing started at a velocity of 12. It slowed down continuously all the way to rest. And I want to know how far it got in that. And it did so for 3 seconds. So it slowed continuously down from 12 to 0 in 3 seconds. I want to know how far it got. So what I realize is, okay, on average, it was going 6 meters per second. 6. There's a number that I didn't know was relevant until now. And it did so for 3 seconds. So I think in the end of the day, the answer is 18 meters. 18 meters. Yeah, that's the answer to question A. Question A. How far does the object get in the first 3 seconds of this constant acceleration? I think the answer is 18 meters. Now that number makes sense to me. I think I just explained it, but let me be clear. I mean, at least at this stage or this method, I don't just see that in my, okay, I sort of do, but I wouldn't expect us to just see that number in our head. Like it's not, that number is not 4 times, that number is not 3 times -4, nor is that number something that just obviously got read off the graph. It's number 18, right? If you want to see where is that on the graph, and again though, so I'm saying it took a little work to get that number 18. Hopefully it's clear, or at least hopefully it makes sense. Nicholas, where's Nicholas? No, just kidding. Hopefully it makes sense, but I don't think it's self-evident, right? And let me also caution you again, always in physics, there's 2 states of mind that tend to happen in physics to all of us, students and teachers at any age. Cool. Awesome. I love that guy. All right, that's awesome. And he was paying attention. All right, that's like a triple portal. Thank you. And I believe him because it does. But you know, one of the reasons it also helps me that he does that, and other people should, I'm not just trying to praise him, but like why I like that feedback is because what I also know, I know from personal experience, whether you've noticed this or not, the thing about physics that's weird and deceptive and either super cool or super annoying and intimidating to all of us is that at any given moment in physics, when an idea is first presented, generally at first things are like, if they are slightly at all confusing, then they're really confusing. Like, wait, I don't know what's he, I don't even get that. Wait, what? And then the thing about physics is the minute something does make sense, because physics actually really does actually try to make sense. Once we understand something in physics, the problem is it makes so much sense, and then we immediately think it's obvious. The problem in physics is that zone of satisfaction where you're like, oh, I get something hard. Good for me. And wow, I just learned something hard and interesting. That zone, which you should experience all the time, you get deprived of all the time. Because what tends to happen in physics until you really start looking out for this situation is what happens in physics is people tend to go from, huh? Wait, what? I have no idea what you're to all of a sudden going, oh yeah, that makes total sense. Oh yeah, of course. Like, duh, I'm a total idiot. Yeah, no, of course. Like I knew. And then like immediately you're like, why didn't I know that the whole time? I'm an idiot, I'm a jerk, or he's a confused. Like people, once you get it, you think you knew it the whole time because it makes that, but no, you got to realize. So what I'm trying to say, that's awesome. No, and if you're having that experience ever, Felicia or Nicholas or anyone, or anyone, then welcome to the club. If every moment you finally understand something, if you then go, oh, I'm an idiot. Oh, of course, duh. No, really, honestly, you're not an idiot. You're good. It feels that way because physics makes that much sense and because you are that smart that you got it. But
You're the one favors products, less than one reactants. Okay.
Was that, oh, okay. So anyway, so please, every time you do get something, please do not self-deprecate. Please pat yourself on the back and say, oh, I do get that now. Now, one thing about this, I want to show you that you get the 18 meter number. Like, could it be read directly off the graph? No, but is it in the graph? Oh, yes. Like, is the graph useful? Oh, yes. Like, where is this in the graph? Well, notice if you go to the graph, yeah, look, well, if you go to the graph, look at this. Now, some of you may recognize this from calculus. If you look at the area under the curve, under the straight line, under the boardwalk, the area between our actual graph and the x-axis, if you look at that triangle, right, like the area of a triangle is 1/2 BH, 1/2 the base times the height, right? The base of this is 3 and the height of this is 12. 1/2 of 3 times 12 is 1/2 of 36, right? Or in other words, it's 1/2 of 3 is 1/2 times 12 is 18, or 1/2 of 12 is 6 times 3 is 18. I'm saying, what is 18? 18 is the area of that triangle right there between the graph and the x-axis. That's what 18 is. Like, what? Like, well, first of all, if you remember any calculus, this is not a coincidence because velocity is the derivative of position. Therefore, velocity is the derivative of position. Therefore, if you want to read how far you've gotten in positions from a velocity graph, you want to go backwards. Like, velocity is the derivative of position. Therefore, position is the antiderivative of velocity. Position is the integral. Oh, I said it. But yeah, right? Position is the or displacement, when it change in position, is the integral of velocity. The integral is the area under the curve. Now, so those of you, so it's not a coincidence at all that the area under, sweet. Oh, and he even like hiked it to a colloquial level. Yeah, facts, like this is actually deep and cool. And really, again, I know that everybody in this room has a different relationship with the word integral or the term area under the curve, whatever. Like, for some of you, this, like, I know it's hitting you on different levels. And for some of you, the minute you hear the word integral, you don't want to say facts, you want to say vomit. Like, I understand that. But partly that's because the integral never like had any place to sit in your mind. What I'm trying to say now is that there's something that these ideas do connect. The position is the integral of the velocity. It's the area under the curve of velocity. But what does all that mean? I mean, what 1/2 BH? What the heck does that? What it really means is, think about it. What really just happened is, what we're saying is that displacement is of average velocity times time. And average velocity is the first velocity and the second velocity added together divided by 2. The second velocity here is 0, right? So the average velocity is half of that initial velocity times the time. Half of the initial velocity times the time. Half of one dimension, like, or the other way around, multiplication is commutative. Half of the time times the initial velocity. Half of the base times the height. Pardon me for 1 second. 1 second. Oh, okay, okay. Yeah, well, actually, pardon me for 1 second. I'm sorry. Things are happening. A million things are happening. Dogs are barking. Integrals are being taken. Okay. Wait, and something was happening in the chat. I think I read all the chat, but I'm not. Oh, cool. Facts. Me and Lev. Okay. Okay. So 1/2 BH. What that really means is 1/2 of velocity times time. And why 1/2 of velocity? Because it's the average velocity times the time gives you displacement. It all actually, so the answer is 18. It kind of does make sense. Now I'm going to show you one more thing about this 18, where like I just did a lot of work to get that 18. I am trying to emphasize that some work does have to be done to get that 18. If you're given the acceleration, like what we always want to know in physics is how far did something get in a certain amount of time, or how much time does it take to go somewhere? Like it's always space, time in physics. But what I'm trying to emphasize here is if you have the information acceleration, then you do have the information you need to get displacement, but you always have to realize it's 2 steps away. Acceleration is the second derivative of position with respect to time. So you never get it directly. You have to do something. Now, I just did a lot of work, partly because I'm still trying to explain, and also because I did it the sort of the long way that I think makes sense, but it is long. Can you shortcut all of this work? Yes, the shortcut we've done. The shortcut is, just to remind you, sorry. Whoop. Oops, sorry. Like what we just did, we did x equals at average velocity times time, but then we had to take this side road to realize that final velocity was acceleration plus initial velocity. I'm just trying to show you what I already did show you last week, but maybe it makes more sense now that we've done 3 examples. I'm just trying to show you that if you take the whole process that we just did, which was saying, okay, displacement equals average velocity times time. Okay, average velocity is initial plus final. Oh, I don't know the final. Oh, I better use the acceleration to figure out the final. If you just put that all together algebraically, what we just did, if you just did it in steps without the numbers and just looked at it as one big algebraic process, you would get that equation that we got a week ago. That's the point of that equation, is just to compress the whole process we just did and allow us to do it in one fell swoop. In other words, here, what we could have said, and now, and once you get this, I think it is faster to just use this equation, but I'll also caution you, I don't think you should just plug and chug into the equation until you really see what it's doing, or you, like in theory, you could always do it without the equation if you really understood what was going on. I'm just saying here, if we want to solve directly, we could have said 1/2 a -4 times 3 plus 12 times 3, right? Like you could just plug straight in, but if you were, you would be doing what we just did, just a shorter way. 1/2 times -12. Oh, sorry. Oh, wait, hello. What did I just do? That was weird. Oh, sorry. Square, right. And there's the 18 right there. Okay. And notice it is the same thing. It's literally what we just did, only in one step, because we combine all the steps into one. That's the power of algebra. Okay, but that's where your 18 really means half. It really means that you started off with the speed of 12. What this is really saying is we started off with a speed of 12. If we just continued that for 3 seconds, we would have gotten 36 meters. But every moment we were losing our speed. So it's really how far we would have gotten without losing speed, 36 plus, or in this case, minus plus whatever we lost due to the loss of speed. And what we lost due to the loss of speed was 18, because on average, we lost, um, 6 meters per second, and we lost that for 3 seconds, which makes 18. But anyway, all right, so that's the answer to that. We've got 10 more minutes and the dog is going crazy. Hold on a second, let me just see. Okay, hold on. We're gonna just do one more thing and then stop for today, but actually I think we're getting a lot done, I believe. I mean, but tell me if that's not clear, but here we go. Oh, you know what? Okay, I guess I will bang through. You're going to complete this tape. Well, yeah, I think I could just, yeah, okay, I think I can just quickly finish this. All right, so this is not going to be interesting, but just hopefully maybe helpful. That was all question A, B. So I'm just going to do this quickly, just finish this problem for you. I think if you're with me, I think you'll find the rest sort of straightforward. Like B, determine the displacement of Edna for the first 6 seconds of her journey. Okay. Sorry. Yeah, I'm going to say, right, I think it's 0. I think it's literally 0. I think I think if you just plug back into the equation, you can check, like, but if you're seeing what I'm trying to say about this, I'm saying this whole graph, this whole situation, what you want to be picturing at all times is exactly what would happen if you threw something straight up. It went up and then came down. Only here the number happens to be -4 instead of -10. But this is all what would happen in a round trip of gravity. Everything would be symmetric and patterned, just like you would hope it would be, because the acceleration is always the same. We're always losing the same amount. So what I think is in the first 3 seconds, yeah, I think this thing started with 12 meters per second. It lost 4 every second. So it took 3 seconds for it to get to nothing, i.e. if we threw it up, it took 3 seconds to get to a peak height. And then it took the next 3 seconds to come back down to where it started, to come back down to a downward velocity of -12. So I think by the end of 6 seconds, it is precisely where it started at 0. Now, I'm just saying that because I think that I'm conceptually looking at this whole situation. I think I now, due to my graph and my first problem, have a conceptual grip of the whole situation. So I think the answer is 0. But you can, if you want to check or practice, do the exact equation I just did. Just plug in 6s instead of 3s, and I think you will find 36 -18. You'll get 36. Yeah, you'll get 70. You'll get -72 plus +72, 0, I believe. So that's but you should check. So that's the answer to that one. I think C, determine the instantaneous acceleration of Edna at precisely 3. Oh, this is a good question, actually. At precisely 3 seconds, if you look at the graph, that's right where it crosses the x-axis, right? Right where it crosses the x-axis, the velocity sure is 0. Like that's the peak height. That's where the thing stopped. But this question is asking what's the instantaneous acceleration? And the acceleration, the slope of this graph never ever changes. The acceleration everywhere, including at t equals 3, including at the peak height, including when v equals 0, the acceleration is -4. That's important. You could read that off the graph. You could do it with the equations, but same thing. If I throw something up and then it comes back down, when it reaches a peak height at that one moment, it's neither has positive velocities nor does it have negative velocities. For one moment, it is at rest. It is a velocity zero, but that doesn't mean its acceleration is zero. If its acceleration were also zero, that would mean it had zero velocity and not changing its velocity. It would hover. So even at the top, even when your velocity is zero, your acceleration still better be what it ever was, in this case, -4. In other words, this is another example. Acceleration and velocity are not the same thing. You could be accelerating while you're not even moving. Please note that. So that's the answer to C. I'm going to D, is Edna ever speeding up? Yes. Edna is speeding up. Edna is the object here. I don't know why we called it Edna, but Edna is speeding up when velocities are getting increasingly negative. Right, when the velocity numbers are negative but getting bigger and bigger in magnitude, i.e., the last 3 seconds, that would be like Edna falling back down, right? And then E, I'll do this, and we're going to stop. We're actually going to stop 4 minutes early, and we are. Yes. Hopefully that's good for everybody. But to complete the table, like I'm going to just sketch this, but like, the velocities are, well, all the accelerate. So this is V, A, displacement. Oh, actually, I might have to save this for next time. Well, I'll complete this, but you check my work and you tell me what you think. I think I'm not going to explain it. I'm just going to tell you. I think the accelerations are always -4. That's the point. Constant acceleration, always -4, right? The velocities go down 12. You know what? I should give myself more room. Sorry. I'll just do this a little bit neatly and then we'll all go. So E. So the velocities are going like this: 12, 8, 4, 0, -4. Now, I'm picturing throwing something up, and it falling back down, but I don't know where I'm standing. I could be standing on a cliff. I don't know. All I know is that the acceleration is continuing forever. It's a constant acceleration. So this pattern has to continue forever. So if the pattern continues forever, that would mean the thing keeps going, right? I mean, no one said, all we know is it's got constant acceleration. And the displacements, okay. So this is, I think, first it's going 10, then it's going 6, then it's going 2, then it's going -2. Oh, sorry. I'm spacing out. something, I have to think about that for a second. I don't know what, sorry, what is going on? I know we are going to leave them one. I may do that jerk thing. Did I just skip a number? What? Okay, yes, okay, I see people are leaving already. Well, I'm going to leave those numbers like that for the moment. You can complete them, or we'll pick up on this next time. I don't want to hold you over class, but those numbers are correct so far, and then we'll go from there. Because I was going to say you could leave early, but you
Have a
didn't.
good day.
So sorry. So you can, oh, sorry. Okay, thank you. Okay, thank you very much. Thank you. Have a good day. And that,
Bye. Have a good day, Professor.
thank you very much. And bye. And I'm going to leave too because